Alright friends, welcome back. In this video we're going to go ahead and take a look at the next section of your textbook, which is P.5, and that talks about rational expressions. So I actually recorded this video once and tried to upload it to Microsoft Stream, but it had all sorts of issues with it. That's why it wasn't available Friday. And then Schoology was also having issues, so I've decided to just go ahead and re-record this video, which actually turns out not to be such a bad thing because the first video was pretty long, and I realized that after taking another look at this lesson that it involves a lot of the things that we have talked about in previous videos, and those are the things that I don't necessarily need to spend a lot of the time on. So in this video, like I said, we're going to talk about rational expressions, what they are, how to find the domains of them, and then how to do operations with them like add, subtract, multiply, divide. So let's get started. So a rational expression is what? Well, basically it is a fraction of polynomials. Okay, or in other words, it's a quotient of two polynomials. So here's some examples here. You have stuff like 1 over x, and then you have x plus 1 over x minus 1, and then you have others, as well as that third one that's sitting there. What we want to be able to do is basically do everything that we've talked about with other types of functions and expressions. We want to be able to do operations with them, and later on we're going to take a look at them as functions and talk about their graphs and that kind of thing. So for right now, it's a good idea to kind of get our ideas about rational expressions under our belts. So let's first talk about domain. So domain has always meant it's just the list or the set of numbers that you're allowed to plug into your function. And since each one of these rational expressions has a denominator, one of the things that we need to think about is dividing by 0. Okay, so that's something that we can never do in mathematics, and so when we talk about the domains of these types of functions, that's definitely the main thing that we need to keep in mind. And so it says right here, to find the domain of a rational expression, you just need to set the denominator equal to 0 and solve, and then just say that your domain is everything but that. Well, I think it's pretty easy on these three functions up top to find their domain, which is what the example down at the bottom asks us to do. So let's go ahead and first talk about the expression 1 over x. Okay, so if we were to do the domain of that, the denominator is really straightforward. It's just x, and we know here that x is not allowed to be 0. Okay, one of the things that we need to kind of practice ongoing is this idea of interval notation, because it's going to come up over and over and over again. Okay, and so to express that using interval notation, we would need to do the union of two sets to exclude 0. And so here's what I'm talking about. So the domain, which typically we let be represented by a capital cursive letter D. That would be the union of these two sets. So you would have the open interval from negative infinity all the way up into the value that we don't want, which is 0. And then we would want to unite that open interval with the open interval from 0 all the way to positive infinity. And so this is something that you guys talked about whenever you first looked at interval notation. This is just the union of two open intervals like that. And it just gives us a way to exclude every value that we don't want. And in this case, that value is 0. So if I were to draw the solution set here on a number line, it'd be really straightforward. I would just go ahead and make an open dot there on 0, and then I would go ahead and shade everything to the left and everything to the right in that solution set. Okay, so multiple different ways to represent the domain, but we would prefer the interval notation there. If we were to take a look at the next one up above here, that was the x plus 1 over x minus 1. It's the same thing. So x plus 1 over x minus 1, we know by looking at that denominator that the denominator is not allowed to be positive 1 itself, because that would make the denominator equal to 0. So our domain is very similarly written to the last one. We just want the union of the open interval from negative infinity all the way to 1, and then unite that with the open interval from 1 all the way to positive infinity. Okay? That very last one up top, the one that says x squared minus 3x plus 2 all over x plus 4, for that one, again, it doesn't matter what the numerator says necessarily. It just matters that we look at that denominator so that we figure out what values x cannot take on. And because here, I believe it said, I keep having to come up here to look at it, x plus 4. There we go. I'm so forgetful. There we go. Okay, x plus 4. We know by just mentally setting that equal to 0 and solving the denominator, x is not allowed to be equal to negative 4, because if it was, it would make the denominator equal to 0. And so our domain here, again, is going to be set up almost identically to the other ones. It's just going to be the open interval from negative infinity all the way to negative 4, and then we will unite that with the open interval from negative 4 all the way to positive infinity. Okay, so when they ask us for the domain of each of these functions, they're all very similarly written. We just need to find that problem value that's going to make the denominator equal to 0, and say that our domain is everything but that value. Okay, so that's pretty straightforward. Next up, I want to talk about simplifying expressions. Okay, so simplifying rational expressions, what it says here to do is factor the top and the bottom and then cancel any common factors. Okay, so just to save time here in the video, I'm not going to go through meticulously all the different steps for factoring all these polynomials here. That would be something by the time you see this video, I would expect you to be able to do. So I'm just going to go ahead and simply write the factorization of the top and the bottom, and then we'll continue. So the top there, it says x cubed minus 4x. If you factor that completely and correctly, you should be getting factors of x and x minus 2 and x plus 2. Okay, so if you need more about more information about how to factor polynomials, I believe that was in our P.4 video. So go ahead and check that one out. So we'll go and put that over the factorization of the bottom, which should be x minus 1 times x plus 2. Okay, so the reason that we want to factor everything first is because now what we want to do is look at the numerator and denominator and find any sort of common factors that they have. Because if they do have any common factors, since we're just dealing with a bunch of multiplications between factors and the fraction bar is just division, we could start canceling some things out. And here we see that we have a copy of x plus 2 in the numerator and denominator, and so we can go ahead and write x times x minus 2, and then that is all over x minus 1. Okay, and so as far as simplifying, that would be acceptable right there. I can go ahead and box that. You could distribute that x back in, so I'll say or here. That would be another acceptable way to leave your answer, x squared minus 2x all over x minus 1. Okay, so again, the reason that I point out multiple different representations is just because, you know, if we have a test and there's multiple choice, I just want you guys to be able to pick it out when you see it. Okay, so for these next ones, again, I'm not going to really go deep onto the factorizations of these, but I will say that in the top, if you factor that correctly, you should be getting a factor of -1. And it looks like my pen is not writing here. Oh, there it goes. Okay, so -1, which I'll just represent by that negative there. And then additionally, in the top, you'll have factors of x minus 4 and x plus 3. And then in the denominator, when you factor that, those are going to have factors of x minus 4 and 2x minus 1. Again, if you need more help with factoring, then feel free to always ask questions, come see me, or watch that last video that we had. Okay, and so when you're looking for common factors here, it's pretty simple. I think we have a pair of x minus 4s in common, and so we'll cancel those out, and finally we'll just have the expression negative quantity x plus 3 all over 2x minus 1, which is one of our answers. That could be one representation, or you could distribute that negative back inside, and you could have your answer written in that way too. So negative x minus 3 all over 2x plus, or sorry, not plus, minus 1. There we go. Okay, so simplifying expressions, pretty straightforward. It does pretty heavily rely on your ability to factor polynomials. So again, if you need more assistance with that, I would encourage you to go back and watch our last video. Multiplying rational expressions. This is basically going to build on what we just did, because what we want to do is simplify everything first by doing that whole factorization process, and then canceling out like terms, and then multiplying what remains. So in order to do that, again, I'm not going to dwell too deeply on each of the factorizations here. I'll just go ahead and write them out. So if we are first looking at this top polynomial on the left, if you were to factor that, that would factor into x plus 1 times x plus 4. The bottom of that is just the linear term, x plus 3. That doesn't really have any factors, so I'm just going to go ahead and write another copy of that, x plus 3, and then times. If we factor this right here, that is a difference of squares, so we can go ahead and write that as x plus 3 times x minus 3 factored. And then that denominator, this is one of your perfect square trinomials. And so we can write that as x plus 1. We could write this as squared, but for purposes of being able to see what we're about to do next, I'm going to go ahead and write 2 copies of it multiplied. Okay? And so now we're here. And again, what we now want to do is exactly what we just did for the last couple of examples. We want to look and see where we have like terms that can cancel for us. We're looking for one on the top and one on the bottom, of course. Okay, well, we have a matching set of x plus 3, so I'll just go ahead and get rid of those real quick, one on the top, one on the bottom. And then, again, the reason that I wrote this out as 2 copies of x plus 1 in the denominator there was so that we could see one of those copies cancels with the one on top. And I don't believe anything else cancels there, so we can go ahead and write our final result here. This is going to be factors of x plus 4 times x minus 3, and that is all over x plus 1. and that is something that we can just go ahead and box there. You could expand that all out for the other representation of your answer there, but that's not something that we'll have to do. Okay, so that would just be foiling out the top, and then you're finished on that. Dividing rational expressions is pretty much identical to multiplying because we can redefine division in terms of multiplying by the reciprocal, okay? And so we can go ahead and rewrite this problem simply as x squared minus 16 over x squared minus 2x, and then we can write this as times the reciprocal of what we were dividing by, okay? So we're just going to go ahead and take this rational expression and treat it as the fraction that it is, and then flip it upside down. So on the top we'll have x squared minus 4. On the bottom we'll have x squared plus 6x plus 8. And there we go. Okay, anytime you divide rational expressions, we will go ahead and convert that division to a multiplication by the reciprocal. Okay, the next step of this work would be to go through and factor absolutely everything, which again, I'm not going to bother showing the work for here. I'll just kind of talk through it. So if we were to look at this top polynomial right there, that's x squared minus 16, that's a difference of squares. We can simply write that as x plus 4 times x minus 4. Okay, in the denominator of that rational expression, that looks like that has something that is a GCF, so we could factor out an x from both of those terms. So we can say x times the quantity x minus 2, and then we'll say times, and then we'll do the other one, right? So if we're looking at this polynomial right here, that's the x squared minus 4. That, of course, is a difference of squares, so we'll say x plus 2 times x minus 2. And then in the denominator here, this polynomial right here, that is not one of your perfect square trinomials, but that is a trinomial that we know can factor into the product of two binomials. So we'll say x and x for these first different spots here. And then we are looking for two numbers that are going to add to 6 and multiply to 8. Pretty easy to find those. I think that we'll just find those in a positive 4 and a positive 2. Okay? And so now looking at everything factored, it's easy to go through and find out what cancels for us, which is now what we want to do. We've got a copy of x plus 4 in the numerator here that's going to cancel with this copy in the denominator. We have a copy of x plus 2 here that's going to cancel with that copy in the denominator. And finally, we have a couple of x minus 2's that are also going to cancel for us. So you can start to see the importance of being able to factor everything, because once you do, we can just go ahead and write what remains, and that is our final answer right there. So anytime you divide rational expressions, really easy to set up. You just multiply by the reciprocal. After that, you want to factor everything, cancel out terms, and then write the rest. So getting into this topic of complex fractions. So complex fractions are rational expressions with additional fractions in the numerator and or denominator. So this is like fractions within fractions. And so in order to simplify, we're going to do exactly what we just did, and we are going to always look at this fraction bar between our two rational expressions as division, because, well, that's what it is, okay? And we just talked about how to handle division. It's just multiplying by the reciprocal. So I'm going to go ahead and take that top rational expression, that x squared minus 1 all over 4x, and I'm going to convert that yellow fraction bar there to multiplication as long as we do it by the reciprocal. So we're going to flip that bottom rational expression upside down. We're going to have x cubed over x minus 1 quantity squared, okay? And so now what we want to do to just go ahead and simplify the rest of this is factor everything and then see what cancels, and then we'll write the rest, right? So this top polynomial right here, that is a difference of squares, x squared minus 1. We could write that as x plus 1 times x minus 1, and then that is over 4 times x, which that's the best we could really do as far as factoring something like 4x is concerned. And then we'll say times. Now that x to the third power, I'm going to go ahead and, for purposes of this example, just to show you, I'm going to go ahead and write that out using the definition of exponents. Just if I have x cubed, that just means I have 3 copies of x all multiplied out. And then finally, instead of writing x minus 1 quantity squared, I'm going to go ahead and write both copies here. So x minus 1 times x minus 1. And you guys probably see where I'm going with this, but again, we've been doing it all video. We just want to see what cancels now, right? So looking for common things in the top and bottom, we have a pair of x plus 1's that cancel. And the reason that I wrote out the x cubed is because we see now that I have a copy of x and a copy of x that's going to cancel here as well. So what remains here, of course, is going to be x squared. And so we'll write that out, right? We'll say x squared times that quantity x plus 1 in the top. And then on the bottom, what remains is 4 times the quantity x minus 1 in the bottom, okay? Now again, this could be one version of your result, but it's not as expanded as we may like it to be, so I'm going to go ahead and say or here, and then just distribute in the x squared in the top and distribute the 4 in the bottom. So My final answer could be here x to the third power plus x squared all over 4x minus 4 if I distribute in the top and the bottom there. So two different representations for our final answer in this example, and this is how we're going to go ahead and talk about complex fractions, is always in this way. All right. So if we look at another one here, this is another type of complex fraction that you can run up against. You'll notice that there's not a lot to do here in the numerator here, but definitely stuff to do in the denominator. We're actually subtracting two fractions in the denominator there, so we're going to need a common denominator in order to go ahead and work with the rest of this. So we'll just go ahead and write the x minus 4 from top. But then on the bottom, we want to go ahead and get a common denominator, and the easiest one to go with is just going to be the one that we get when we multiply these two existing denominators together. So we're going to rewrite both fractions so that they have denominators of 4x instead of just 4 or x independently. Well, we all know how this goes, right? We would just need to introduce what they are missing to both denominators, which means we also need to introduce those to the top. So this becomes x squared over 4x minus 16 over 4x. And now that they have a common denominator, we can go ahead and write that with just one denominator. Okay, so x squared minus 16 over one copy of 4x. That is completely under the x minus 4. Okay, now how are we going to work with the rest of this complex fraction? Well, we are going to pick up with exactly what we just talked about. This division fraction bar here, we are going to write as a multiplication as long as we do it by the reciprocal. So we have the x minus 4 from on top, which I'm going to go ahead and include a set of parentheses because we no longer have that fraction bar to kind of separate the top with the bottom. I'm going to go ahead and change that to multiplication, and we're going to go ahead and do it by the reciprocal. So 4x over x squared minus 16. Okay, now I'm going to continue working down the page here. The next thing that we would want to do is exactly what we've been talking about, which is to go ahead and factor everything and then cross out terms in the top and the bottom that match. Well, that is a difference of squares there, x squared minus 16. So we're going to go ahead and, oops, I wrote 16 there, I meant 4. There we go. We're going to go ahead and write that out, and we will see here definitely that we have a copy of x minus 4 and x minus 4 that cancel. And so our final result here is going to be 4x all over x plus 4, and we will go ahead and box that as our final answer. Okay, so complex fractions, that's just another way to look at dividing rational expressions. Complex fractions come up from time to time, so it's important to know how to deal with them. All right. We can also add and subtract rational expressions, and because they're just fractions, it's just going to mean that we're going to have to find a common denominator if there isn't already one, okay? So it makes examples like this really super easy, right? Especially this part A, we already have a common denominator of x minus 3, so we just want to go ahead and combine those two numerators into the same numerator, and we'll get our final result that way. Not too shabby. For this next one, we are taking the rational expression 4 over x plus 2, and we're trying to take away 7. Well, we know we can't really combine these unless this 7 had a denominator of x plus 2. But if I introduce that to the bottom, I'm also going to have to introduce that to the top. So I'm going to have to multiply the top also by x plus 2. Okay, and so we have a common denominator now, and so what we can go ahead and write here is simply 4 minus 7 times x plus 2 all over x plus 2. Okay, and what we would want to do is just simplify that numerator here a little bit. Really easy to do here because we have 7. We're just going to go ahead and use distributive property to distribute that in, and then we'll combine some like terms here. So we've got 4 minus 7x minus 14, and that is all over our common denominator. And so finally combining those two constants there, we're going to have negative 10 minus 7x all over x plus 2. Now that is one way that we could write our result, but you'll notice that both of the terms in the numerator both have a negative 1 factor in common, so we can go ahead and pull that out. So we'll say negative here, and I'll rearrange my terms here as well just so the x comes first. I'll say 7x plus 10. That would be equivalent to what we had in the line before. So there is our result right there. Next one down, the two denominators look very similar, but they're not exactly the same. Remember that subtraction, the order matters when you do subtraction here. But it's no problem because if you were to just go ahead and take a look at this expression, this is equivalent to factoring out a negative 1 from both the 4 and the x. Okay, so if we were to do that, then that would mean that the x would become positive and the 4 would become negative. Okay, and so one way that we could do this is we could go ahead and say that this is simply just, and I'm writing this upside down here, but stay with me, 5 over x minus 4 plus negative x minus 4 underneath a 7. And now we almost have like terms there as well, or common denominator, I should say. Really, the only thing that we need to introduce here is going to be a factor of -1 in the denominator of the first fraction, which means I just need to also introduce it to the top. So that effectively becomes -5, and I've got -5 plus 7, which is going to make 2, and so I could write my final answer as 2 all over -x minus 4, which is one way to leave your answer, but typically we would like to go ahead and put that negative on the constant that's on top. So my final answer here, I might say, is -2 over x minus 4. And that might be a little bit of a cleaner result for us there in that problem. So again, working with rational expressions, adding and subtracting, you just need a common denominator, very simply. Okay, you might have one like this, and again, the main thing to do is you always want to factor. Okay, so when in doubt, you just factor everything out. So if I go ahead and do that here, I've got 3x over, that is a difference of squares, so I might say x plus 3, x minus 3 in the denominator of that first fraction. Okay, and then I'll say minus here, and then we're going to have 5 over the product of two binomials, because if that trinomial factors, then that's what it's going to factor into. And the leading coefficient there is simply just 1, so I know that this is x and x. And now I need two numbers that are going to multiply to +3 but add to -4. I think that is going to be pretty simple if we just do -1 and -3. Okay? And so now what we'll do is we'll look at our two denominators and we'll decide what they have and what our common denominator would be. Well, it looks really, straightforward here that we have three different types of linear factors in our denominators here. We've got an x plus 3, we've got an x minus 3, and then we've got an x minus 1. So the common denominator would be the one that I get when I just multiply all of those linear factors together, one copy each. So my common denominator might be the x minus 1, so that it's represented, and then the x plus 3, so that it's represented, and the x minus 3, so that it's represented. Everybody that shows up in a denominator is going to be represented here in our common denominator. Okay, well, we're going to need to change some of these denominators here to accommodate this. So it looks like that first denominator is missing that copy of x minus 1, so we'll introduce it to the bottom, which of course means we have to also introduce it to the top. So we will go ahead and do that. And let's just write what the result would be there, because if we were to actually do this, we would have to distribute that monomial 3x to both of the terms of that binomial there and multiply that out. So what would that be? That would be 3x squared minus 3x. Okay, so that's good. We'll hold on to that. Next, we're going to take a look at the other rational expression and decide what it's missing in its denominator. It looks like we're missing that copy of x plus 3 here, which means we'll also introduce it to the top, x plus 3. And why not? Let's just go ahead and distribute that in as well. And be careful what we're distributing in here, because this is a minus sign, folks. And so we need to distribute in a -5 instead of just a +5. So that'll be here -5x minus 15 for us. Okay? And so now that we are looking here, we have some like terms that we can combine. So we can go ahead and say x squared minus 8x minus 15. And I will allow you guys to go ahead and leave that denominator factored. We don't need to expand that out. It's not that you couldn't, it's just we get the point by now. We'll just go ahead and box that as our final result there. And that's it for that problem. Okay, so again, taking a step back and looking at what we did, we factored everything. We had to get a common denominator, so we had to introduce the linear factor that our denominators were missing to get the new denominator, and then change our numerators accordingly. Okay, and so here's another example here that I'm actually going to skip because it's almost identical to the last one. The only thing I want to say about this is remember that this is a difference of squares here, so when you factor that, that becomes x plus 2 times x minus 2. And so you can pretty easily see there that we've got linear factors of x plus 2 and x minus 2, and this already has both of those, and so it would be really easy to find a common denominator on that one. Okay? Expressions with negative exponents. Okay, so again, don't forget how negative exponents works. We reviewed this a little bit whenever we went over exponents, but it says here, factor the expression by removing the common factor with the smaller exponent. Okay, so what does that mean? Well, we just need to identify where the smaller exponent is, and then maybe remind ourselves of some of those exponent rules so that we can make sense out of how it would factor out here for us. Okay, and so when you look at this immediately off the bat, it doesn't seem like there's much of a common factor, but there really is. Okay, because if we factor out, let's say, an x to the -3rd power, and then write what our leftovers would look like, let's maybe try that. Okay, well, this x to the 7th, we just factored an x to the -3 out of it. So what could we possibly write here? Well, whatever we write there, remember kind of working backwards that if I were to distribute this back in, that would be taking a base of x times a base of x, which would mean that I would have to add those exponents, and my result would have to be 7 when I do that. Well, one way that you could think about this is just by thinking about that very addition and realizing that that would be 10, okay? Because again, if I were to distribute in an x to the negative third, then that would have to be adding those exponents, so I'd have to say negative 3 plus 10, and that would give me the 7 that I started with in the very beginning. And so you kind of have to think backwards a little bit whenever you factor out a negative exponent like that. But that's exactly what we would want to do. And then finally, because that second term had a copy of x to the negative third in it, we could just go ahead and say that the leftovers for that second term are simply just going to be minus 6, and that's going to be it for us, okay? So that's going to be our result factored there, and we'll just go ahead and box that. So not too shabby. This one down here, taking a look at some things that it has in common. It looks like we have a base of 1 minus 5x in common in both of those terms. So let's maybe go ahead and factor out one of those. So we're going to factor out the one with the smaller exponent in it, and here that is going to be negative 1/2. Because now when we write our leftovers, which I'm going to write a big parenthesis for, let's see what we have. Well, in that first term, I had x times what I factored out here. So what I just leave behind is x. And then finally, I've got my plus sign, so we'll say plus. And then when you think about that next term, remember what we're looking for. We are looking to if we were thinking about going backwards, we're looking to multiply that back in so that the exponents would add and give us a 1/2 here. So let's just say plus. And I'm going to go ahead and say, give me a copy of the base. Really, the only thing that we need to think about is what does this exponent need to be such that if I were to add it to a negative 1/2, I would get what I started with, which is positive 1/2 up here, okay? You can set that up as an equation if you really want to, but it would just be the equivalent of just saying, well, what is 1/2 plus 1/2? And here that would just simply be 1, okay? Which I'm going to go ahead and write here for emphasis, okay? And we know that that exponent of 1 really doesn't ultimately matter, so I'm going to go ahead and write my GCF that I took out, and then we'll write what's left over here. Well, since that's just 1, I can drop these parentheses, and now I've got some like terms to combine. I can go ahead and write these leftovers as 1 and then minus 4x. Okay, and that would be the simple factorization on that one. So it's a little bit awkward to think about whenever you have negative exponents in the mix, but we just need to kind of think in terms of what we've always thought in terms of, right? Which is when you multiply like bases of x, or maybe in this case, like bases of an expression like 1 minus 5x, you would always add those exponents. So you're going to have to kind of work backwards a little bit and maybe do some subtracting to make some sense out of that. But there's the assignment for P5 right there. I hope this video has been of some help to you. Always feel free to ask questions in class or to send me a quick message on Schoology. But that's all I've got for this one. Thank you very much for your attention, and I will speak to you in the next one.